Kristin Zimmerman of the Society for Experimental Mechanics to discuss experimental mechanics and its role in science and engineering today. Kristin is currently the treasurer of SEM. She's also the executive editor of SEM Proceedings and the SEM Handbook series, which River Publishers is responsible for. And Kristin is also the former president of SEM, as well as other key positions in the past. So thank you, Kristin, for joining me today, and let's get started.
Thank you, Brent.
So let's start at the beginning. What first drew you to experimental mechanics?
Thank you. That kind of kickstarts this discussion, and I'm going to do one half of a step backward to what is experimental mechanics. It's like, what is this? Because nobody really understands. What's that? No, I don't work on cars, but actually I do because I like cars, but it has nothing to do with that.
Nice.
What it is I describe it as applied physics. Why? Because a lot of folks understand physics. They've heard that before. And physics is a pure science. And it's one that studies more, nature and natural foundational elements of science rather than application. So what is applied physics in that sense? It's more the application of physics to solve scientific or engineering problems. Aha, engineering. You'll find that all of our members, most of the members of SEM, which Society for Experimental Mechanics, have a background in mechanical engineering, physics, aerospace engineering, civil engineering. So yes, there is a profound engineering space there, but it's taking that physics or the real creative, got to figure out why things happen as they do in nature and be able to apply them to be able to create things that, in the technology and science space that, build things. And also the applied physicist or experimental mechanician has a deep role in being able to understand the fundamental elements of, say, a structure or a material, such that if that material were to fail or that design were to fail, who would you call on? Quite likely somebody with an experimental mechanics background, because we understand this pure elements, the foundational elements of solids and materials, such that we can we've already developed techniques, but we can use those techniques to determine why something failed, such that it can be designed differently going forward. So maybe that answers a couple things in your list here, but back to kind of coming full circle to what drew me to experimental mechanics. Well, I was at Michigan State University. I was a physics major, and I did not know that I really wanted to be working in a laboratory my entire life, and I would probably have to achieve a PhD in physics, and then I would likely go on to teaching or into a research lab, and I wasn't sure what I wanted to do. So with physics, I picked up mechanical engineering, and I ended up getting a degree, a Bachelor of Science degree in mechanical engineering. But I kept the major of physics, and I kept following with physics while I was in my engineering degree. And then upon graduating, I didn't know what I wanted to do. Market wasn't really hiring, engineers widely at that time. So I thought, all right, let's move into, a master's. Let's pursue a master's. Well, where did I land? Well, I landed in, at the time at Michigan State, there was a department of material science and mechanics. And I met a professor. And how did I meet that professor? And you're going to find this to be the case with most of the members of SEM. We come in through academia because of, a great working relationship, collegial relationship with a professor, our advisor. And I was introduced to Professor Gary Cloud from one of his PhD students who happened to be teaching a laboratory that I needed to take in my engineering class. And it was a statics lab. And I did well in the laboratory, so well that instructor asked if he could introduce me to his PhD advisor because they needed an additional lab hand, let's call it,
Okay.
help her out, in the lab. And that really kind of laid the foundation for my then PhD in experimental mechanics, and really guided what I learned. And it was something that kept me curious. Again, always going after that, why do things happen as they do in nature? And also stimulating, the application side. I found that a lot of like-minded individuals that I met, because Gary Cloud introduced me to the Society for Experimental Mechanics. Of course, I came in as a student. I presented a paper. It was a student paper competition that I was in. And I learned of, who else attends these meetings, and what are they talking about, and what are they working on? And the society and its members embraced me as a very young, studying graduate student, and intimidated by all of these giants. I meet the people that wrote my textbooks, and I'm thinking, wow. And they come up to me and they share a cup of coffee, or just have a chat. And I'm thinking, wow, these people are really nice.
Right.
So,
right.
very humble and mentors. And they're asking me, how I'm doing with my studies. And if I ever need any help, don't feel, afraid to reach out and ask for guidance. And I'm thinking, this is very, very unique. And that helped to define, that the society as the friendly society. And it tended to, as I'm finding with many other members, it tends to keep you coming back for more conferences and
Right.
being as participatory. So that's
And
a little bit of the background.
Yeah, I did notice that at the IMAC conference. I've been to a lot of conferences over the years in publishing. And what struck me at IMAC was how well everybody interacted with the students. Because I've
Yeah.
seen students chase people just trying to get a minute, but it was the exact opposite. It was people, experienced professionals, academics, who were directly engaging with students. And that was fantastic. So I'm glad that you brought that up, because I noticed that myself at the conference. So that's really great. Um, okay. Knowing that you're talking to a communications and English major, what's your go-to description of experimental mechanics? And let me just say this, okay? The first thing that pops into my head is from my high school days when the space shuttle exploded. And they said it was the O-rings, I believe it
Yes.
was.
Mm-hmm.
Is that a good example?
Quite likely the people that did the analysis to determine it was the O-rings had a background, very strong background in experimental mechanics.
Okay.
Yeah, and of the time, way back when, we didn't have, composites per se. It's pretty much metals. Everybody knew isotropic materials, and we knew the constitutive properties of steel. I could mix it with a little bit different, whether it be a nickel or some other type of metal. But we knew metals. But then, you migrated into these other composites, that are Kevlar blends, glass blends, carbon blends, and on and on and on. They don't respond the same way. They don't fail the same way.
Right.
They can be designed for lightweight, but they're going to fail completely differently than an aluminum or a steel structure. So, yeah, that would be part of how you could explain it to somebody. Why did something fail? Who can answer that? Somebody who has a strong background in experimental mechanics, which means during their engineering, probably during mechanical engineering, you take 3 classes that are a requirement: statics, strength of materials, and dynamics. You have to have 3 different semesters or quarters, let's say. Those are the foundational teaching tools, the foundation of mechanics, those 3 classes. And then you take them. And so what engineering fields have to have them? Well, a handful have to have these 3. They're kind of like weeder courses. If you can't pass these courses, you're not going to get an engineering degree.
Okay.
You have to have them. And so everybody understands statics, strength of materials, and dynamics. And then, so what did the mechanician do? Well, how do you measure the strength of a material? Okay, we developed all of the tools. that, in the early years, it was strain gauges that could actually measure what? Stress of a material and
Mhm.
strain. Strain would be how much it can deform before it fails. So can it deform? And then there was this, does it deform elastically or plastically? Well, think about it. Elastic, kind of like a rubber band. It goes back to
Mhm.
its original form. But if it deforms plastically, oops, you just went past the ability to go back to its original form. So, so the terms kind of made sense. And then you get into these shape memory alloys, which are really, really cool because you can bend them and twist them and whatever, and they'll spring back, to their original form. So there's some really cool exotic materials today. But back in the day, as you find some of our original members, they worked on the Apollo. I mean, they were the individuals that did the testing on the materials to determine whether or not it could sustain the forces required to do the job.
Right. So that would include things like heat shields for coming back
Absolutely. Yep.
into the atmosphere and so on and so forth. Okay, because I was just listening to Elon Musk saying we're testing what parts of the heat shield, what if this fails, what if that fails, and talking about testing to the point of failure to see where that ledge is. So these would be experimental mechanics people doing this kind of work.
Quite likely, or like I said,
Mhm.
engineers, but they've got a strong background in those three fundamental areas. So they've got a good mechanics voice. And being an
Right.
experimentalist, they apply that pure science
Mhm.
and to develop new things.
Oh, so this goes beyond just testing what exists, but then helping
Oh,
to create new materials. So
absolutely. Very
that's
much so.
okay.
And then once you have a new material, you can't use those previous testing methods necessarily. So with that new material, you will have to design and define the parameters for testing its strength
Hmm.
or strain or, deformation, all these things, because it's new.
Right. So and I'll just use a very base example. So when carbon fiber became a thing, you and your colleagues had to create new ways of testing because it just acts differently than other materials do.
Absolutely. And
Okay.
another example, because it seems to be talked about in the last decade more and more, is additive manufacturing
Okay.
and 3D printing. Like, wow, I can make this part in a few hours and I can put it into my vehicle to replace something else, which
Hmm.
typically would be a metal part, or it could be a
Right.
rubber part, let's say. But okay, you just manufactured this in a very, very different manner. And you mix some, maybe some polymers with some structural metals or something, it's definitely a composite. So it
Hmm.
may look exactly the same as the previous part, and it may function, therefore, the same, but maybe only for a certain period of time, then it fails. Well, why did
Yeah.
it fail? Because, okay, you put it into an environment that is expecting a metal, because it's say a metal or metallic environment or a high heat
Hmm.
or high temperature environment, and maybe it can't sustain the heat thresholds. It looks exactly the same, but it's
Right.
not. You created it differently. So through these new, not necessarily technologies, there's a bit of technology in there, new models, new designs. Some of our members say, this is really tapping into my laboratory. Maybe we should create a new technical division to find out who else is working in these particular areas. Because again, the experimental mechanic individual is constantly learning. You probably also witnessed that at IMAC. Why were these people
Yes.
talking together? Because
Hmm.
they have this insatiable thirst for learning, and nobody feels better than another because there's something yet to learn. So it's a completely different mindset that the mechanician goes in with, saying, all right, let's get a team together. Let's learn together, because, the forces of multiple minds will be able to figure out something far better than somebody working in a vacuum.
Right. Absolutely. Just a quick question because things pop into my head. Are these the people that as kids knocked down the Lego towers and then rebuilt them and then knocked them out to see what different, or, the bridge experiment. I know that that's a popular thing in mechanical engineering, build a bridge and see how much weight you can hang from it. Was there a joy in breaking those things? Or is that what it is? Because I know electrical engineers who took apart radios when they were kids to figure out what each constituent part was. Is there, I see, it may be a very simplified way of thinking of it, but I see experimental mechanics as breaking things, seeing what the breaking point is. Where can we take this? Is there I won't say, I will say joy, but I don't mean it that way. Is there joy in breaking things?
Um, I I don't know. I wouldn't say that there is a joy in breaking
Mm-hmm.
things. Um, but again, you hit a chord with that because I was different. Just speaking personally, I was different as a child. My
Mm-hmm.
mother always reminded me. It's like, yeah, they sent us home from the hospital earlier because you were taking apart all the cribs.
Mm-hmm.
It's
Mm-hmm.
like, yeah, I took everything apart.
Yeah.
She would come home and I would have the oven completely taken apart, or the washer, or one
Mm-hmm.
time it was a good chunk of my vehicle
Oh no.
because I needed to learn, I wanted to fix something that was broken,
Yeah.
or my curiosity for trying to understand how it worked. So is that an innate thing with experimental? And probably it's innate to experimentalists. I really didn't know I was an experimentalist until,
Right.
I actually got a degree in experimental mechanics. I
Right.
knew I loved physics. I mean, that was
Mhm.
my love of how things or why things were as they were in nature. That was different from the get-go. And so
Yeah.
maybe I bet if you interview others in the experimental mechanics community, you may find that to be a common thread.
Mm-hmm.
We're a little
Well,
bit different, curious, and yes, things would break, but then we try to figure out why, and then we would redesign it.
right, right. So what we're really talking about is a lifelong fascination
Yeah.
with all of this, and that's fantastic. And is well, let's go there real quick. You told us about your experiences as a student and what advice are you giving or would you give to students coming through the academic setting, the university setting, that suddenly find this? What kind of advice would you give to them to further their career?
It's really interesting. Remember, it was a lab instructor who happened to be working in a particular area. That was kind of cool.
Mhm.
And so he introduces me to his advisor, and that advisor happened to be a member of SEM. So,
Mhm.
and he was an experimental mechanician. And so, did he recognize something in me?
Ah,
So it's almost like the secret of success is being ready when your opportunity comes, but you don't really know what that is. Is it prescriptive? No. But the experimentalist, I think, has a wider, huge breadth to thinking about more what's possible rather than what's probable.
mm,
It's a
yeah,
much broader view on observationally
right,
what's
right.
around them. I would just, again, say that for myself, a curiosity, and I see it in the other members of SEM. And
Mhm.
why does SEM become like the home society for its members? It's like a family reunion. We're all of like mind almost. I think we
Right.
found people that are like us.
That's really interesting way of saying it. Again, my first experience at IMAC was a very familial experience. Everybody knew it. Nobody knew me, of course, because it was my first time there, but everybody knew everybody else. There was so many, hey, how you doing? How's this going? And they seemed to know each other's experiments that were happening. That family atmosphere to me was because I've gone to so many conferences. That one seemed to be the most friendly that I've been to. So, that's really fantastic and way to go.
And it was
Um,
smaller. It was much, SEM is a
exactly.
much smaller community, and we get about 150 to 200 new people coming to our conferences each year. And who's bringing them? Well, likely a professor or a lab instructor that's been in SEM for a while. So it's somebody who's, mentoring this new community. And once we get these young graduate students involved, they'll stay involved through their academic career. They'll graduate. And we lose quite a few if they go into industry, because industry doesn't necessarily support or see the importance of continuing something that might be too academically based. But if the individuals move on into an academic career or a research laboratory, the chances are, and we're now tracking this a little bit closer now in our member database, is they stay with us, and then they continue to bring others along.
Yeah, it's almost viral how everything works. You get people in, you get people hooked, and then they stay forever. And that's exactly what you're looking for. And that's fantastic. That's fantastic. So let me ask you this. What's the part of experimental mechanics that hasn't changed? Is there a part? I mean, maybe things are adjusting constantly and you never know, but is there a soul of experimental mechanics?
Yeah, there is, and it's the people.
Okay.
We are, that is the soul. We are of like mind, and we are constantly learning, and we want to impart that and embrace others, bring them along and mentor. There's no ego. It's really interesting. I try to, what is this? It's like we have no ego. We're like full of super ego. We just want to share and learn together. So that's quite a different approach. You go and give a presentation, and it's not, you want to present it well, but the most exciting part is the Q&A and the discussion in the hallway afterward, because you piqued the curiosity in somebody else and you follow up on it. And it may be a relationship that you continue for the rest of your professional career.
Now, with the rise of AI and all that's going on in industry, academia, doesn't matter. AI is just becoming synonymous with every engineering and science and whatnot. Are you seeing the same at SEM? Is AI affecting anything at all, or is it having a giant effect?
Yeah, that one, the first thing that popped in my mind with AI is it certainly assists the theoretical aspects of mechanics, computational, because anything that can accelerate that. But the experimentalist is a hands-on individual. It's a person thing. Yes, it can crunch some data for us quickly and maybe combine data sets for us in that sense. But the experimentalist has always been, way back in the day when modeling started to interplay, and finite element models. Oh my gosh, they were going to be the be all end all, and they could answer all the problems that you have when you're trying to design something that doesn't fail. And then what happened? Oops.
They failed.
They failed. So then they realized, oh no, you can't throw the baby out with the bathwater. Oops, we got to get some of that experimental stuff back in here. Why? Because models are built on assumptions and design parameters. Well, where'd they come from? Out of the blue? No, they came out of the laboratory. They came out of experiments. So then when they used the experimental data to help define the criteria that was going into the model, guess what? The model got a lot better. And both work wonderfully well together. Neither one is good on its own. It's just going to work for you on its own. So AI will help, but it will never replace.
That's fantastic. So yeah, I think I heard the other day that people who are welders, electricians, plumbers, so on and so forth, AI will never replace that.
Nope.
So this is the same. Since it's hands-on, you have to do it that way. You absolutely have to do it that way. You can't model all this to see what's going to happen. So yeah, that's really fantastic. How do you see SEM's role in shaping the future of the field, or is it status quo? But again, research is becoming much more global, much more digital, and interdisciplinary. So what do you see SEM's role as in the future?
Yeah, we will continue to convene, individuals that need help solving a particular, maybe very enigmatic research problem or an applications problem. We won't change in the sense of our fundamental soul. That will continue. The thing that I really have enjoyed watching over the last decade is individuals will come in and say, here's a new problem. It's a little spin-off from something that's very fundamental, but it's a new application and we need help. They'll start talking with the colleagues at a conference. They'll give a paper, and then there'll be a little bit of energy behind it. And it's like, okay, the following year, they'll say, we want to set up a session, or maybe a half a day or a day of sessions at the conference. Well, then it starts bubbling up. Next thing you know, they become a technical division and become a key area of focus for the society. We can do that because we're so small, and
Right.
because we have the individuals, they come with an idea, and we can facilitate. The structure of headquarters and the way that the business is set up, we can quickly respond to that. And even in the additive manufacturing area, it's being worked on in mechanical engineering and Society for Automotive Engineers, a whole bunch of other professional engineering societies. But they're not looking at, and I apologize, my kitty cat's trying to contribute here.
That's okay.
But what they're overlooking is the mechanics of it. And what if it fails? And they're like, oops, the design worked perfectly, and our model said that it should work just fine, but it's not. Well, so that's where SEM said, hey, we have a role to play here. They're really
Right.
overlooking some key fundamental areas of mechanics that should not be overlooked, or there could be some real dire consequences. So, okay, what happened? We've now we formed a new technical division. And it kind of spun out of folks from the national laboratories that were working with universities. We're a very academic group, but not exclusively. I mean, a lot of labs, research laboratories across the globe were extremely global. We always have been. Again, if a professor might do a sabbatical, they go to school in the US, but they'll do a sabbatical in Europe or Asia or South America, chances are they'll bring back a few students with them. And then all of a sudden we grow a laboratory or, a set of working colleagues in other countries, and then it just starts to grow from there. It's very organic how it grows.
Yeah. Now, I understand that it's very academic, but there's also a practicality that industry, government, so on and so forth, can tap into at any time because, I used to work for a company called Plastics Design Library. And additive manufacturing, of course, is huge in the plastics industry, and everyone was at. But when you say, oh, well, we can produce this for 30 cents cheaper per unit, which ends up being millions of dollars a year. But the problem is it no longer contains so let's say you're making containers of mustard. I can get the containers for less because of a different polymer that they're using. But the problem is that polymer and mustard don't mix.
Yeah.
They don't work together. And you've just spent millions of dollars coming up to this, and then guess what? It fails completely. So there is a practicality to what SEM is doing that then translates out into, I'm going to say, the real world, for lack of a better term, because I know universities are the real world, but it gets out into the corporate world as well.
Yeah, and for industry, we do have industry members, not as many clearly as the academicians and those from the national laboratories. But if we have an industry folk or person there, they're likely working in the research laboratory of that industry, like General Motors Research or Dow Research or Boeing or such like this. And then there is, with our conferences, especially IMAC community, there's a large exhibitor component. So what are they exhibiting? They are exhibiting the tools and sensors and testing equipments that live in the experimental mechanics community. So with the IMAC, it would be more structural mechanics, dynamics, modal things, because IMAC actually originally stood for International Modal Analysis Conference. But for the annual conference, those are more solid mechanics folk. So they're looking more at the static strength of materials dynamics components of it. So one is more applications. IMAC's clearly more applications oriented, but the vendor component is really cool because they'll work with our members, and our members may co-define and co-design a new piece of equipment. And that is indeed what happened when, the fundamental technical divisions of SEM in its early years were optical methods, strain gauges. These were all measurement tools. Now, optical methods was more non-contact, non-destructive testing, where with strain gauges and some of these tensile tests and such like that, they would be destructive testing. Right. Well, one of our members, he also was a president of the society, and now he's a member of the Academy of Engineering as well. He designed, with his colleagues, a new approach, new set of instrumentation called digital image correlation. It's an optical method, but it is a non-contact whole field. It can look at a whole system and look at where the stresses and strains, deformations, all of this information comes in now optically, digitally. So we moved, kind of in the AI world, we moved into the digital world of being able, rather than high-speed cameras, it was another digital method for bringing in information. And he designed and defined that approach, and then one of our vendors started making the instrumentation for it. So we are the founders of digital image correlation, we SEM, because of one of our members.
Nice. So just again, I'm visualizing things. So if you have, let's say, a piece of carbon fiber and it's in a machine that twists it, would the digital image be shown? I'm foreseeing like blue is okay, orange is bad, red is bad, is worst. It's about to break. Is that kind of like? Does that make any sense at all to you?
Yes, it does. Okay. It does the color coding, and the different bands of color would indicate. Photoelasticity was one of the very, very early things, and that was all colors because it would use polarized or unpolarized light to shine through and determine where the stresses were in a lot of times plastics or some kind of hardened plastic material. In fact, Dr. Cloud, you'll find a lot of professors in experimental mechanics do a lot of consulting work for companies because companies want to know what failed and why. So it was a company actually that said that Ziploc, I think it was, had infringed on one of their patents for their Ziploc bag. And so in the laboratory, I ran the tests and we designed the experiment. We all designed the experiments. And you could see the residual stress within one of the Ziploc bags. And did it match the residual stress in the other Ziploc bag? If it did not match, then they were actually manufactured differently and there was not an infringement.
Wow. Okay. So this was actually evidence for a court case.
It was evidence for a court case. Yes. So a lot of that stuff going on because, well, we are forensic investigators in many ways of being able to determine, and we were using an optical method. We were using a polariscope at the time. And I thought that was really, really cool. And again, I was in my master's and I was being supported on a research, not a fellowship, but a stipend to help me with grad work. And so Dr. Cloud would give me, these things that he was working on. We'd work on them together. And it was a wonderful learning platform because it fed off of my curiosity, how things work. And he taught me in the other area that he was working on was Moray interferometry. And you think, Moray interferometry, and that sounds like a really big word. What's that? Well, it happens in nature. So how do you use this? So it's kind of an optical illusion. It happens in nature, but how do you use that to measure deformation and strain in materials? And so that's what Moray interferometry is. and you use lasers and all this kind of cool stuff.
Right,
And I thought
right.
that was actually the PhD research that was being done that I was asked to come in and assist with.
Mhm.
And I thought, wow, I better go get my master's to figure out, I know how to do this stuff, but I don't know, the math behind it, and I don't know the true science behind it, but I knew how to do it in the laboratory
Yeah,
to be able to conduct an experiment. So
yeah. I was going to ask if you were involved in an experiment that has had a lasting impact. That's the best
yeah.
example. That's just so cool. And the fact that it was used in a court case for people who love that kind of stuff. That's me.
Oh,
But
yeah,
the fact that you could prove, no, they're using a different manufacturing method because
yeah,
of this test. And
yeah.
that's really, really interesting.
By the way, this area of residual stress, which we did see in the optical, pattern that was on this,
Hmm.
residual stress is, I don't think there's any other field that talks about residual stress other
Right.
than experimental mechanics. And it is
Oh, okay.
profound. It is absolutely profound. It was like, oh, let's use this metal. It's coming in, 30% cheaper or 30% lighter. It's like, well, how did they form it? Because all of a sudden
Yeah.
it starts forming cracks, because it was heat treated wrong, or there was a residual stress that had formed in that particular material, which
Hmm.
made it not worthy of being able to handle the stress and strain.
Yeah, absolutely. It reminds me of a recent example, the one submarine that imploded was
Mm-hmm.
supposedly made out of carbon fiber. And, I don't want to get into anything that's legal aspects or anything like that, but my understanding is if they had just used stainless steel, it could have gone where it went and would have had no problem at all. But since carbon fiber was new and cool and everyone was impressed by it, but the problem was once it got to those depths, it was over. So, this is absolutely fascinating, Kristen. I can't thank you enough. And, I certainly hope that students will follow similar path to what you did. And that's why you're involved in SEM right now, is because someone led you down the path. And I know you're enjoying yourself. I know that you got so there's,
A lot of energy.
exactly, exactly. And that's absolutely fantastic. This is what we want to see with everybody that's involved in applied science and engineering and everything else, is just, again, that lifelong fascination is what moves the world. And
Yes, I agree.
that's phenomenal. So I can't thank you enough. We're out of time. Again, this is amazing, and I thank you. If there's anything else you'd like to add before we leave.
No, I'm good for now, because as you probably already know, I could continue to talk about this for hours. So
Yeah.
I thank you for letting me talk as long as I did.
Yeah, yeah. Well, next time we do this, I want to get Wendy and John and other people involved in this because I want to see it from all the other perspectives. But you provided a fantastic introduction to experimental mechanics and SEM. So thank you so much. I hope you have a wonderful day and the rest of the week. All right.
Thank you, Brent.
Thank you, Kristen.